The equation obtained by equating a physical quantity with the dimensional formula is called dimensional equation of the physical quantity. What are the fundamental quantities it depends on, and what are the powers to which each of those quantities are raised? Now these are the fundamental units and the fundamental dimensions. We know N2 U2 is equal to N1 U1. Inside a sine or cos function, you know that you should have an angle, you should have a theta, angular displacement. Hi students, welcome to Infinity Learn by Sri Chaitanya. I'm Aniruddha, your physics faculty, and today we're doing a quick take on the dimensional analysis. We learn what it is, what the dimensional formulas are for certain important quantities, and then also see how to solve questions based on those dimensional formulas. So let's get started. Before we move into the formulas and everything, we need to understand what dimensions actually is. Now there's two ways you define dimensions. There's one dimensions which you call as 1D, 2D, 3D that define in how many directions your actual motion is. But over here, this dimension actually tells you how any quantity depends on the fundamental quantities. What are the fundamental quantities it depends on, and what are the powers to which each of those quantities are raised? So what are the fundamental quantities? We know about fundamental quantities. There's mass, length, time, luminous intensity, amount of substance, so on. There's a number over there. And with each of those fundamental quantities, we have associated its own dimension. For example, for length, the dimension is represented with L. Now whenever we are representing dimensions, we'll keep it under inside these third brackets. That way we know that this L is not a variable. This L refers to the dimension of length. Similarly, dimension of mass is represented with M, that of time represented with T, exactly as the letters. Besides these are the fundamental quantities. We have more fundamental quantities. We have electric current, that is dimensionally it's given by A. Temperature dimensionally given by K or theta, and these go more with their units. For example, the SI unit of current is ampere, SI unit of temperature is Kelvin. So it comes from there, the lettering comes from there, but if you put it in third brackets, it just means that you're telling that the dimension of electric current is A. Luminous intensity CD, again from candela, and amount of substance is mole. Now these are the fundamental units and the fundamental dimensions. Most derived quantities will be combinations of these fundamental dimensions. So let's learn about that. The dimensional formula, the expression which shows how and which of the fundamental physical quantities represent the dimensions of a physical quantity is called the dimensional formula of the given physical quantity. We'll see what it is. The equation obtained by equating a physical quantity with the dimensional formula is called dimensional equation of the physical quantity. So right off the bat, if you're not introduced to this might not make sense. So we'll look at quite a few examples, and there you will understand this in detail. So it says we need to find the dimensional formula of these quantities over here. First one, we have height, width, radius, displacement, and all of them, what are they? They are just lengths. Whether you consider it as height, whether you call it width, radius, whatever, you're measuring length. So the dimensional formula for all of them is just L, because there's just a dependence on length. Next up, we have area. And when you think of area, then that is, suppose you're thinking of the area of a square. What is that? The formula is side square. Even if you're thinking area of a circle, it is pi r square. So everywhere you see there's that r square, there's that a square, which means there's that length squared. Any length quantity is squared. Wherever you look for an area, even rectangle, length into breadth, which is also a length. So it's a length squared. So the dimensional formula of area is L square. Okay, we can even keep the 2 inside, because certain textbooks keep the 2 inside. And I think even in NCERT we have this inside, so we can keep it like this. So that is L square. Now this is the dimensional formula. This is the dimensional formula, and as soon as I equate it with the quantity, it becomes a dimensional equation. Okay. Next up, we have volume. What is the formula for volume? It is length cube. Why? Because volume of a cube is a cube. Volume of a sphere, 4/3 pi r cube. Then you have, even for a cone. For a cone you have, or for a cylinder, it is pi r square h. R square is length square multiplied with h, which is another length, you again have L cube. So whenever you're finding volume, its dimension is going to be L cube. Next, we have density. Now what is the formula for density? Density rho is equal to mass divided by volume. Now dimensional formula of volume is L cube. Dimensional formula of mass is m. So dimensional formula of rho becomes ml minus 3. ml to the power minus 3. Mass divided by volume. Dimensional formula of mass by dimensional formula of volume. Let's look at a few more. Here we have velocity. What is velocity? Velocity is distance by time. So that is distance which has the dimension of L and time which has the dimension of t, which makes this as Lt minus 1. That is the dimension of velocity. Next, acceleration. Acceleration is what? Velocity by time. Velocity is this. When you put another time below, you will get it as Lt minus 2. Right? So that's acceleration. Next, linear momentum. What is linear momentum? It is mass into velocity. So velocity we already know, multiplied with mass. So that gives me ml t minus 1. That is the formula for linear momentum. See, it's like I have one of them and I am deriving from there on based on what formulas I have. Okay. Next up we have force. Force is what? It is momentum by time or mass into acceleration, whichever way you go. Let's say we go with mass into acceleration. So acceleration is this, multiplied with mass gives it as ml t minus 2. Okay. This is one of the main formulas you need to remember, because like I said, from one formula you can derive multiple ones. Like I know velocity, from there I could go to acceleration, momentum and so on. So force is one of them that you should remember even if you don't recall. These are easy to get to. But for more complicated systems, you'll see the dimension of force and energy that we'll learn right after are important to remember. So here we have work or energy. What is the work? Work is force into displacement. Force we got as mlt minus 2. So work would be equal to mlt minus 2 into L, into distance L. So that makes it ml2 t minus 2. Next up, power. Power is energy by time. So that is equal to ml2 t minus 3, because t minus 2 divided by time, t minus 3. Pressure. Pressure is force divided by area. So it's mlt minus 2 force divided by area L2. That makes it ml minus 1 t minus 2. Next up we have angular displacement. Angular displacement means theta, and theta is actually r by s. My bad, it's s by r. It's s by r, arc length by radius. This is also length, this is also length. So you have L by L, that makes it L to the power 0. So dimensional formula of angular displacement we write as L to the power 0. Now L to the power 0 you need not even write. You can even represent it as t to the power 0, m to the power 0, whatever, because this is what we call as a dimensionless quantity, because it has no dimensions. There's no length also. I'm just representing L to the power 0 just because I need to write something. It does not have any dependence on length. As you see, the L factors cancel out. So quantities like this, where there is no dependence on any fundamental quantity, are called dimensionless quantities. Okay. Next up we have angular velocity. Angular velocity omega is theta divided by time. So theta is dimensionless, but you still have 1 by t dependence, which makes the dimension of this as t to the power minus 1. Next up, torque. Torque, as you will learn, torque is equal to F into R. Force into the radial distance. It's going to be similar to work or energy, because there also it was force into displacement. So this is also ml 2 t minus 2. Okay, mainly you need to remember force, but if you occasionally remembering this energy also helps. Okay, these two you should remember. Mug them up or whatever, but these two you should have, force and energy, because everything else can be derived from there. Next up, what are the applications? There are two main applications that we look at. First up, it's to check the dimensional correctness of any equation. If an equation is given, you have to ensure that the dimensions of each term in the equation have to be the same. Which means if you have, say, C is equal to A plus B, then the dimensions of C, A and B have to be the same for this equation to exist. Okay, it does not happen with multiplication or division, but as long as there's addition or subtraction, all of the terms, if you had minus E over here plus D, all A, B, C, D, E, all of them should have the same dimensions. If you have, say, over here F by G, then F and G may have different dimensions, but F by G as a whole should have the same dimensions as D, E, B, A and C. Okay, let's look at a question now. This one says force is given in terms of time and displacement x by the equation F is equal to A cos bx into dt. Now C sine of dt. Now over here we need to find AD by B, which means we need the dimensions of A, B and D. First up, inside a sine or cos function, you know that you should have an angle, you should have a theta, angular displacement, which should be dimensionless, which means dt should have no dimensions. It should be, let's call that L to the power 0 only. So dimensions of D would be this, say theta divided by t. So dimensions of D should be equal to t to the power minus 1. Right, so we've got the dimensions of D. Next up, we need the dimensions of B. Now again, over here, let's do it here itself. Bx should be equal to some theta. Dimensionally, it should be equal to theta from a dimensional point of view, right? Which means B is equal to theta by x. X is length. So dimensionless divided by length. So B becomes equal to L minus 1. And over here, this cos or this sine, they are again dimensionless because they are just they'll give you dimensionless quantity. Sine or cos is going to give you dimensionless. So dimensionless quantity multiplied with one A over here gives you the dimensions of force, which means A also should have the same dimensions as force. So the dimensions of A would be ml t minus 2, right? So we need AD by B. So AD by B would be equal to ml t minus 2 into dimensions of D. What are the dimensions of D? T minus 1 divided by dimensions of B, which is L minus 1. That makes it ml2 t minus 3. ml2 t minus 3. This is the correct relation for it. Okay. The next type of application is over here to convert a physical quantity from one system to the other. So generally, whether you represent, say, 5 kg, right? It is of number 5 multiplied with its unit kg. That 5 kg is the same as 5000 grams. The quantity is same, we're just calling it differently. So what are there? There's the quantity and there's the unit. So we know that the number, the magnitude into the unit should be equal, because the amount is the same, whether you may call it differently, but the amount is the same. So the magnitude and unit, their product should always be equal for the same amount. Okay. From there, if you just shift this, we get N2 is N1, we'll effectively get N2 is equal to N1 into U1 by U2. Now U1 and U2 are the units, which means I can represent them in the fact, say U1 is, dimensions of U1 is m to the power A, L to the power B, m to the power A, L to the power B and T to the power C. Then I can have U1 by U2 in this form, because U2 will also have a similar dependence because they are the same quantities. So then you can represent it in this form, where you will have M1 by M2, L1 by L2, T1 by T2 all raised to their power, where M1 is the unit, fundamental unit of mass that you're defining in that unit measurement, in that U1 measurement, right? Like in kg, fundamental unit of mass is kg, but when I'm defining gram, my fundamental unit becomes gram, right? Similarly, same for length and same for time. Again, we'll understand this with an example. Here it says we need to find the value of 100 joules on a system which has 20 centimeter, 250 gram and half a minute as fundamental units of length, mass and time. So joules means it's a unit of energy, which is ml2t minus 2. Okay, energy is ml2t minus 2. So what do we know? We know N2U2 is equal to N1U1, which means N2 is equal to N1 into M1 by M2 into L1 by L2 to the power 2, because it was ml2 t minus 2, and here you have T1 by T2 raised to the power minus 2, because that is a dimensional formula for energy, which is joule here. Now N1 is, how much is N1? It's given. The value in that first unit system is given, 100 joules. 100. What is M1? M1 is in the normal SI unit, it's 1 kg. So we'll keep it as 1000 gram. The reason we are representing it as 1000 grams because next up we have 1000. Here in this system, in M2, in the U2 system, the defining mass is 250 gram. So we have 250. On this side we have L1 by L2. L1 is 1 meter, which is 100 centimeter, divided by L2 is given as 20 centimeter. That is the fundamental in this one. Don't need to keep the centimeters. Here we have square, and the time in the normal case is going to be 1 second. It's 1 second in the normal SI unit, but in T2 it's half a minute, which means it's 30 seconds. This is minus 2. So let's calculate this out. Cancel out, you get 4 here, this gives you 5, and you have 30 square up top. So it's 100 multiplied with this 4 multiplied with 5 square gives you 25 into 30 square, that is 900. What do we get? We get 4 into 25. This again gives you 100. So this is equal to 9 into, you have 2 here, 2 here and 2 more here, 9 into 10 to the power 6. That, so 100 joule in the SI unit is equal to 9 into 10 to the power 6 joule in the unit where these are your defining or fundamental values of the mass, length and time. Okay, so this is how you find the conversion. So that's it with regards to our discussion of dimensional analysis. Go ahead, practice more questions, because this is a comparatively easier chapter, but from where consistently questions come every year in almost every paper that is there. So go ahead, practice more, and I'll catch you all in the next session.